Our next topic is directional derivatives, and the idea is very similar to what we called partial derivatives. Partial derivatives were very special. There was something, something fixed about them. We only look at the x direction and the y direction and the behavior of the function along those directions at any point. Okay? Does everybody understand why I'm doing this? It's not my dancing talent. But what if you want to look at a different direction? Suppose you want to look at this direction, like 45 degrees between the x and the y axes. Okay? And then you can still look at the behavior of the function along that specific direction. That's going to be the directional derivative. So here's the definition right away. So the first thing you want to do is prescribe a direction. Okay? So that's going to be done using a unit vector, which we're going to denote by u. U hat means it's a unit vector. So u, which is u1, u2, let u be a unit vector. The fact that it's a unit vector means that its length as a vector is 1. So I'm going to write that u1 squared plus u2 squared square root equals 1, but since it's 1, we don't need that square root, right? So that's the property of being a unit vector, and we're going to use that. That's why I'm emphasizing this. Then, the directional derivative of, and this is for a function of two variables, one can generalize it, of fxy at the point x0, y0 in the direction of u is, so the directional derivative of the function at a specific point in this prescribed direction is given by the limit as h goes to 0 of, we're going to divide here by h, and it should resemble what we had for partial derivatives. In partial derivatives, in for example, the df to dx, we only made looked at the local behavior at points near x and fixed the y coordinate, right? And with the partial with respect to y, we allowed y to vary slightly. We took y plus h and fixed the x coordinate. Now we want to allow both to vary, but only along a straight line, which is prescribed from the point in this direction. Okay? And the way to write that is, look at f at x0 plus h times u1, and y0 plus h times u2. And then subtract f at x0, y0. So think about it a moment and tell me, do you agree that this point where I'm evaluating f is a point, well, when h is 0, it's just the point x0, y0, right? But that's not of interest because we're looking at the limit where h goes to 0. But for other values of h, it's x0, y0 plus h times u1, u2. So we're looking at points which are along the line in the direction of u from the point x0, y0. Do you agree? Okay? And this is the directional derivative. So the first thing you should notice that if you take u, I'm going to write that, but I want to first show it. If you take u to be 1, 0, do you agree that 1, 0 is a unit vector, right? And 1, 0 is precisely the x direction. Do you agree? Okay? So if you take u to be 1, 0 and plug it into here, what do we get? We get x0 plus h times 1, so x0 plus h. And here this vanishes because u2 is 0. So we get x0 plus h, comma y0. We get precisely df to dx, the partial. Does everybody see that? And when u is 0, 1, we get the other partial. And for general u, we get every possible direction. Okay, so let's remark that. Remark for the specific u, which is 1, 0, we get df to dx. And for u equals 0, 1, we get df to dy. Okay, everybody see that? Okay, good. Now, the theorem that I want to prove says that under certain good conditions, and the conditions are namely going to be that the function is differentiable, there's a relation, there's the notion of a directional derivative is related to these two very specific ones, to df to dx and df to dy. And that's this theorem. So maybe let's start it on a new board. Theorem. Suppose f belongs. Remember that we said that all our good functions, we're just going to assume straight away that they're C1 in a neighborhood of the point. Remember? Okay. So, but in this case, for example, the property that I'm going to use, I want to prove this. It's an easy proof. The property that I want to use of f is simply going to be the definition of differentiability at the point. Okay. So suppose f is C1 near x0, y0. That's that property. And I'm emphasizing this just that so that we get used to the idea that we're doing here something that's kind of being a bit loose. Okay, so if you want to, maybe if you open a book, you'll find this theorem stated more strictly, in terms of the statement, but in fact allowing more functions to satisfy it. So you may find the theorem saying, suppose f is differentiable at this point. Okay, that's a weaker assumption, right? More functions satisfy that than C1 functions, right? Okay, suppose f is C1 near x0, y0, then the directional derivative at x0, y0 in the direction of u, which is u1, u2, is given by oh, I forgot to write the notation. Stupid. Okay, let me finish the writing the theorem, and then we'll go back and add the notation. The directional derivative, remember the partials were denoted df to dx and df to dy, right? The directional derivative is denoted df to du. That's the notation. Kind of obvious, but one should write it. So x0, y0, the directional derivative is given by the partial derivative, df to dx, at the point, times u1, plus the partial derivative, df to dy, at the point, times u2. Okay? So before we prove this, I want to go back to this board where we wrote the definition and add that this limit is denoted df to du at the point x0, y0. Okay? And of course, the limit doesn't necessarily exist. Like with any limit, when it exists, then it's called a directional derivative. Okay? Good? Any questions so far? Everybody good? Okay. So back to this theorem, I want to prove it now. I want to prove that the directional derivative in a given direction u is prescribed by take the two partial derivatives and multiply the x partial by u1 plus the y partial times u2. Okay, let's go ahead and prove this. So proof. And as I mentioned before, what the main ingredient is going to be the property, what we called star in a previous clip, of f being differentiable, okay, which is implied by f being C1. So remember what C1 means, everybody? Continuous partial derivatives in a neighborhood. Okay, so f at x0 plus hu1, y0 plus hu2, minus f at x0, y0. What we want to show is the limit of this thing divided by h as h goes to 0. That's the definition of df to du, right? Look at that board over there. The limit of this thing divided by h as h goes to 0 is precisely what df to du is by definition. Okay, we want to calculate it. So I'm first looking at this difference, and by the fact that f is differentiable, the property star that we had, this equals a. Remember capital A and capital B? A was df to dx times h. Df to dx, that was the a, times h, times, what was h? H was the increment in the x direction. Remember? We had in general x0 plus h, y0 plus k. Remember that? So h was the little increment in the x direction. So here, the little increment in the x direction is hu1, right? Plus b was df to dy, times k. K was the increment in the y direction, which is now hu2. Plus, that wasn't it, there was this function, alpha of h and k, remember? Alpha of h and k, hu1, hu2, times the root of h squared plus k squared. So hu1 squared plus hu2 squared. Good? So what I wrote is that property of being differentiable. Okay, and we phrased it in terms of specific h and k's, which are multiples of this u vector. Okay, good? Okay, now I want to divide it by h. Okay, so this is, let me add, since f is differentiable. So since f is differentiable, we have this. And this implies, when I divide out by h, that f at x0 plus hu1, y0 plus hu2, minus f at x0, y0, divided by h, that's the left-hand side, equals df to dx times u1, I divided by h, plus df to dy times, that's not a y, df to dy times u2, that's this after dividing by h, plus, and what do I have here? I have, so first of all, okay, let me write it, plus alpha of hu1, hu2, and I'm going to divide by h, but what am I going to write up here? Remember that u1 squared plus u2 squared is 1. U is a unit vector, right? So if I take the h out, what I get here is h squared u1 squared plus h squared u2 squared. I can pull the h out, pull it out of the root. How does it come out of the root? Right, with an absolute value. And what's left is the root of u1 squared plus u2 squared, which is 1. So that's what's left. Good, everybody? Everybody follow that? Okay. And now, finally, I want to take the limit of this thing as h goes to 0. That's precisely the directional derivative. So the limit of this thing as h goes to 0 is the limit of this thing as h goes to 0. Df to dx at that point is a constant. It's fixed. u1 is a number. It's fixed. Everything here is fixed. What about this thing? Right, this is either 1 or negative 1. In any event, it's bounded, and this goes to 0 by the definition of differentiability. The alpha portion goes to 0 as h and k go to 0, and when h goes to 0, both coordinates of alpha go to 0. Do you see that? So this goes to 0 times something bounded, everything goes to 0, or you can argue in terms of one-sided limits, that's equivalent and gives you the same result. So the limit of this thing as h goes to 0 is df to dx times u1 plus df to dx to dy times u2. Good? And that's what we wanted to prove. The limit of this thing as h goes to 0, which is precisely df to du, df to du equals df to dx u1 plus df to dy u2. Good? Questions? Yeah?
So if the partial derivatives don't exist, then the directional derivatives don't exist either?
That's a good question. So the question was, if the partials don't exist, does it imply that the directional derivatives don't exist? And the answer is no, it doesn't. So the formula that we found here in this theorem, okay, says that if f is c1, then we have this formula. When a function is c1, in particular it's differentiable, it has partials. Okay? So if f is c1, it has partials, and then you can find the directional derivative in any direction. It's going to have it, and it's going to equal to this expression. But a function can have only specific directional derivatives and not the others. When it doesn't have all the directional derivatives, it's not going to be differentiable. It's not going to be c1. And you already know an example. Think of that function which gives you the graph of which is that rooftop that we drew several clips ago. Remember that? So the way we drew it, we thought of it as being parallel to the xy axes. Okay? But if you take that building and twist it, no, that's hard to twist buildings. Take your coordinate system and twist it. Okay? Then the building could be the roof could be diagonal to the axes now, and then it would have a directional derivative in this direction. It would have a directional derivative in this direction, but in all the others it wouldn't. And in particular, it won't have partials. Okay? But it does follow from this theorem that if a function is differentiable, we already know that differentiable implies it has partials, the a and the b, but it follows that if it's differentiable, if it's c1, it has all the directional derivatives. Okay? And this should, at this point, you should feel that that's something right, that should happen. Because you should think of differentiable functions, or C1 functions, as smooth. Okay? And when they're smooth, they have a tangent plane. And when they have a tangent plane, in any direction, they're going to have a tangent line. Those are the directional derivatives. Good? Did that compile? Did that make sense? Okay, great. Okay, what I want to do now is do an example. Take a concrete function and calculate some directional derivatives. So let's do that. So here's our example. Let's look at fxy, which equals the cubic root of x y squared. So note that in contrast to most of the examples that we looked at so far, this doesn't have the cases, right? It's not defined differently at 0, okay? And that should make you suspicious. So why might something be not obvious in terms of the derivative? But you know that. Even in a single variable, the function cubic root of x, at 0 doesn't have a derivative. The slope, right, it's the inverse function of x cubed. It looks like this, right? X cubed looks like this. You all know this, right? This is x cubed, single variable. So the cubic root of x is the mirror image with respect to the diagonal. Everybody knows what I'm talking about? So it looks like this. This is the cubic root of x, single variable. So x cubed, the slope at 0, the derivative at 0 is 0, right? Cubic root of x at 0, the derivative is in double quote marks is infinity, right? The tangent line is the y-axis, okay? And the reason I'm doing this is that it's not differentiable at 0. Okay? We don't allow f prime to be infinity, okay? So even this function in single variable has a problem in terms of not being differentiable at 0. Okay? And the same thing is going to happen for this one, and for that reason, we're going to see that interesting things happening. So let's see what do I mean by interesting things. So let's calculate the directional derivative in any direction, in a direction u, where u is u1, u2, of this function at the interesting point, at 0, 0. Okay, let's calculate it. And I'm just going to use the definition. We just had a definition on the board. So I want the limit, as h goes to 0, of the function evaluated at we have to say what, so let u equal u1, u2. I'm not saying what u is yet. Okay, we're going to see that what we get is good for any u. So I need the function evaluated at at x0, which is 0, plus u1 times h, and at y0, which is 0, plus u2 times h. So I need to evaluate the function at xy, where x is u1h and y is u2h. Do you agree? Okay. So what I get, here's the function. Cubic root of u1h times u2h squared. That's the y. Do you agree? Everybody? Minus f at x0, y0. x0, y0 was 0, 0. The value of this function at 0, 0 is 0. So this is the limit that I have to calculate by definition of the directional derivative. Everybody good? Okay. So what do I get? So note that there's an h cubed here, h times h squared, and when it comes out of the cubic root, it's just h. It cancels out with this h, and what I have left is the cubic root of u1, u2 squared, which is h-less. Doesn't have any h's there, so when h goes to 0, it's a constant. It stays the same. So the answer, the limit, is the cubic root of u1, u2 squared. This is the value of the directional derivative in the direction u. And this is true for any direction at the origin. We're checking what are the slopes at the origin. Okay, clear? Everybody? Okay. In particular, what is df to dx at the origin? So df to dx just means plug in for u 1, 0, right? That's the x direction. If you take u1 to be 1 and u2 to be 0. So what do I get? 0, right? Because u2 is 0. And likewise, df to dy. Plug in 0, 1 for u1 and u2. You still get 0 now because u1 is 0. Clear? So here's an example of a function that in any fixed direction you look at over the origin, we don't know what the graph looks like, okay? But at any fixed direction you look at, when you look at the origin, so tell me if you understand my hand waving and maybe body waving. Here's the plane. Here's the graph of the function. I don't know what it looks like yet, okay? But when I look over the origin, at the specific point over the origin, what I see is that in any fixed direction, it has a derivative. And I know the values of the derivative. At the x direction, the derivative is 0. So if I just cut the picture along the x direction, I see a tangent line which looks like this. At the y direction, it's 0. If I cut the picture along the y direction, I'm standing here and looking at it like this, but for you the y direction is like that, right? If I cut the picture along the y direction, look at the derivative, at 0, 0, it's going to be 0. It's going to have a horizontal tangent line, right? And in various other directions, like maybe this direction, if I slice the picture and look at the tangent line, it's going to be some value. It's going to have some slope depending on the direction. Clear? But, we just had a theorem. We even proved that theorem, right? The theorem I'm talking about is this theorem. Look here. The theorem said the directional derivative with respect to u equals the partial with respect to x times u1 plus the partial with respect to y times u2, right? We just found that both partials at 0, 0 for that function in our example are 0, right? Do you agree? Therefore, this right-hand side, this entire expression is 0, no matter what u1 and u2 are. Do you agree? So if this side is 0 and these two things are equal, then the directional derivative should be 0 in any direction u, which is not the case, right? We found that the directional derivative in that example is the cubic root of u1, u2 squared, whatever u1 and u2 are, and it's not 0 unless they're both 0. Do you agree? So this theorem doesn't hold. Do you agree that this theorem doesn't hold for that function? Well, cool theorem, doesn't hold. Only holds. So why doesn't it hold?
It's not C1.
Right. It doesn't hold not because theorems hold only sometimes. If it's a theorem, it should hold whenever its conditions are satisfied. Okay? And the reason that this theorem doesn't hold for that function is that, well, apparently, we didn't prove it, but we're gonna verify that this function indeed is not C1. Okay? And that's why the theorem doesn't apply. It still has all the directional derivatives, and that's even harder to grasp, but it's like the rooftop thing. Okay? But in all the directions it has directional derivatives, and still it doesn't have, these somehow don't fit in nicely, and it doesn't have a tangent plane. It's not differentiable. Okay? So we believe this theorem because we proved it, and therefore, we can conclude here, without proving anything else, we can conclude that f, in this example, is not differentiable, or is not C1 at 0, 0. Because if it were C1, if it were differentiable, it would satisfy that the derivative with respect to u is 0 in every direction because it equals this times u1 plus this times u2. Okay? So it's not differentiable since it does not satisfy that. By the way, another notation for derivatives, I think we mentioned it, but let's throw it in here, is writing f with a little subscript u. This is the same thing as this. It's different notation for the same thing. Clear? Okay. And you'll also see some people write this, f prime u. Okay? So it doesn't satisfy fu equals fx times u1 plus fy times u2, which is the result of that theorem. So if it were differentiable, it would have to satisfy this, and it doesn't. Do you agree? Is the logic here clear? There's a logical argument here. Okay? If it were differentiable, if it were C1, well, let's add here not C1. If it were differentiable, it would satisfy that theorem. But it doesn't satisfy the theorem because this is 0 and this is apparently not. Clear? Conclusion, can't be differentiable. Clear? So let's show, as more practice, let's show that it's not differentiable. Let's show it by definition. Let's verify it so we believe that things are indeed as we claim they are by an abstract theorem. Okay, let's show it. It's not hard. So now I want to show that it's indeed not differentiable, and I'm going to do it by trying to calculate. Remember how we show that something is differentiable? We take that property that differentiable functions have to satisfy, the existence of that alpha hk that goes to 0, and alpha hk has to be something specific, and we check if it goes to 0, right? Let's do that. So let's show that, in fact, indeed, maybe, f in our example is not differentiable at 0, 0. So how do we show it? A differentiable function has to satisfy, I'm going to write it right away with a function. I'm not going to write it with general f and x0 and y0. x0 and y0 are now 0 is 0. Okay, and f is the cubic root of xy squared. Okay, so a differentiable function has to satisfy f at xy, the root of xy squared, minus f at 0, 0, which is 0. Everybody with me? Equals a was the f to the x at 0, 0, but we know that's 0, we calculated it, times x minus x0, but it's 0, so it's not there, plus b was the f to dy, but that's also 0 in our example, so that term is not there either, plus alpha of xy times the root of x squared plus y squared. Do you agree? In general, it should be alpha of hk, but h is x minus x0, and x0 is 0, so it's just alpha of xy. I wrote it here not with h and k, but rather with x and x0, and h being the difference x minus x0. Remember we had that on the definition? Does everybody see where this suddenly landed from? Okay, do you want me to say it again? Okay, the definition of being differentiable was, take the value of f at x0 plus h, y0 plus k. Alternatively, instead of writing x0 plus h, just like in Calc 1, you can just call it x and y, and then h is x minus x0, and y is, h is x minus x0, and k is y minus y0. Remember that? Okay, so this is f at xy, minus f at 0, 0, which is 0, equals a, which is the partial at 0, 0, which is 0. That expression is gone. Plus b times k, but b is also 0. That's the partial with respect to y in the example. We calculated it. So that's also gone. Plus alpha of hk. H is x minus x0. x0 is 0. So alpha of xy. Good? Times the root of x minus x0, x squared, plus y minus y0, y squared. Okay? So this is what has to be satisfied. I have to find the function alpha that satisfies this. Okay? If I find such a function, and I can show that that function goes to 0 as xy go to 0, that's it. Then it's differentiable. So what does that alpha have to be? If there's going to be a function that satisfies this for any x and y, the function has to be the cubic root of xy squared divided by the root of x squared plus y squared. This has to be alpha if alpha exists. Do you agree? So now all I have to do is check. Does this tend to 0 as x, y go to 0? If it does, great, it's differentiable, but that would mean something in my entire argument was completely false. Okay? And if it doesn't go to 0, then cool. Then it's not a differentiable function, and everything we said is true. Okay? So how do I check if this is differentiable? Well, let's try the r theta business. Okay? Let's try writing it as replacing the x with r cosine theta and the y with r sine theta. Okay, so what do I get? I get the cubic root of r cosine theta, r squared sine squared of theta, divided by the cubic root of r squared by r. Do you agree? Okay. And note that here we have r times r squared, which is r cubed. Cubic root is r divided by r, cancels out. So all that we have left here is cosine theta sine squared of theta. Good? Now, what do we have to check? We have to check, does this go to 0 as r goes to 0? Okay? There's no r here, and this does not go to 0. For a fixed value of theta, we get something fixed, and that thing is not 0 unless theta is, I don't know, 0 or pi, which would annihilate this, or pi over 2, which would make this 0. But in any case, in general, this is not 0. Do you agree? So the theorem that we had, f of r times g of theta, where g of theta is bounded and f of r goes to 0, doesn't hold. Okay? That doesn't mean that this thing doesn't have a limit. That just means that converting to r and theta fails. The theorem doesn't hold. Do you agree? But, in fact, looking at this, I can say this function does not have a limit at 0. Why? Because for different values of theta, I get different values. What does it mean, different values of theta? Theta is the angle to the x-axis, to the positive x-axis. That's what theta is in polar coordinates. Remember? And for different thetas just mean fix a theta. Theta equals pi over 4. That's exactly saying we're looking at a specific line and approaching the origin. For different thetas, you get different values, which means along different lines, you get different values. No limit. Clear? So let's write that. So along, or let's write for different values of theta, we get different limits as r goes to 0, as we approach the origin. There's no r here, so the limits are just going to be this thing. This is already constant. And therefore, along different directions, we get different values. Therefore, there's no limit. Alpha xy does not have a limit as xy approaches 0. Okay? So here we just did a bit of practice in calculating or limits or showing that they don't exist. But let's sum up our discussion. This function, by definition of differentiability, is not differentiable at the origin, at the point 0, 0. Okay? Since it's not differentiable at the origin, the criteria for being differentiable is not satisfied. Whatever alpha has to be, it doesn't approach 0. Okay? So it's not differentiable at the origin. Therefore, it doesn't satisfy this theorem, which started with the requirement of being C1 or differentiable. Okay? So it doesn't satisfy this identity, which allows us, for differentiable functions, to evaluate the directional derivative just using the partials. And that's usually going to be very useful. We'll see examples later on. But in this case, we can't do it. It doesn't hold. And in particular for this function, on this board, we calculated the directional derivatives just by definition, without that theorem, and saw that indeed the theorem doesn't hold. Okay, the conclusion of that theorem doesn't hold. Okay? Questions? Yes?
What happened to the cubic root? Like, there is still the cubic root later on.
Where do you see, where are you pointing? Here?
Yeah.
Well, you're right. You're completely right. This should have the cubic root here. You're absolutely right. Thanks. Okay, so fix that, please. But still, it's completely dependent on theta. For different thetas, it has different values. Okay, so thanks. It's a typo, but it doesn't change all the arguments that follow. Okay, good. Okay, so this wraps up this discussion. What I want to do next is introduce a very important concept in this theory, which is called the gradient. Coming up next.